I would have to say that this is my most favorite instruction type of the whole instruction set, and that's the one-shot instructions. The best way to explain a one-shot instruction is that it captures an instantaneous event. Take a carton or an object moving on a conveyor. There is a instant in time when it first breaks the optical path of the sensor. In other words, one program scan, the very first program scan that the photo eye bit went on, that is the leading edge of that object on the conveyor. Then there's the period of time that it's blocking the optical path as it travels. Then there's another instantaneous event, and that is when it clears the optical path of the photo eye. That is, the previous scan, the photo eye was blocked, and on the next scan, it's clear. That is an instantaneous event. Now, on the next scan, it's still going to be clear, but now it's been clear for 2 scans. So a one-shot is a one-scan detection of a change in state. Now, with RS Logics, you had a variety of one-shot instructions, but they were all conditions in the wrong, in the true-false state of the wrong. Whereas the Micro 800 Connected Components Workbench program in the Micro 800, you have a pulse rising contact, a pulse falling contact. So that would be one shot rising, one shot falling in other platforms. Then you also have the same thing for coils. Now, so far we've done a direct coil and a reverse coil, right? Direct coil, rung's true, it turns it on. False, it turns it off. An indirect coil or reverse coil, if it's true, it turns it off. If it's false, it turns it on. Pretty straightforward. But we also have a rising edge coil and a falling edge coil. So when the rung goes true, a rising edge coil will set that bit that it addresses in memory on that scan. The very next scan, it's going to set it right back off because it's a one-shot. So the Micro 800 does give you a few more instructions to accomplish what you want to accomplish in detecting and controlling instantaneous events, one-scan events. So let's get into this. This will take more than one session, but let's get into the first session and get on with it. One-shot functions. This presentation is going to discuss the lab project M13 in part 1 of the CCW Manual for Micro 800. One-shot functions are very interesting. CCW has 6 instructions that revolve around one shot. The basic idea of a one shot is that you want to be able to make a decision based on something within one program scan. You want it to execute either when it starts, the leading edge of a situation. You want to know when it started. So on the leading edge of it, you execute something for one program scan, or on the trailing edge of it. And all of the one-shot type functions revolve around that, whether it be a contact or an output. In the manual, we started with this logic, 2 rungs. We're starting with this instruction, which is pulse rising edge contact one shot. It's a combination of a true if on and a one shot. With some of the older platforms or other Rockwell platforms like 5000, 500, etc., you had a one shot function, and you could integrate that by way of logic into anything. For instance, if we had a true if on down here, we have input, we could add a traditional one-shot instruction right after it, and those 2 instructions together would behave the same as if we did this type of instruction with input 1. It would serve the same purpose. We can also do something similar with the pulse falling edge. So as I said in the introduction, that we want to be able to execute something for one program scan and one only when it occurs and not repeat it until it resets and occurs again. So if we're looking at the rising edge, the instruction that we're actually using, what we're saying is that we want this instruction to be true or have a rung true out state for one program scan only the first time that that instruction goes from false to true. So a false to true change in state of this instruction, irrespective of this bit. Now I realize that because this is a true if on, then it kind of goes hand in hand when this is on and when it's off. But try to keep that out of your thinking. This instruction goes true when whatever in memory that it reads goes on. This particular instruction will only be true for that one program scan when it first detects that that memory location went from off to on. That's because it's a true if on instruction that's pulse rising edge. That means that the rest of this rung, all the way to the output type instructions, the rung will be true for one program scan, roughly less than a millisecond, maybe a half or a third of a millisecond, depending on the size of your program. There are many instances where you need that. Now you can also do that with the falling edge. So let's say that we wanted to know when input 0 went off, not when it went on. In other words, we want to capture that actual instant in less than a thousandth of a second of when it went on or when it went off. These are the two instructions that you can use for that. Consequently, we also have a P and an N down here for output rising edge coil. If we use that instruction, then when the rung goes true, even if it stays true, this instruction is going to set that location of memory to one or on at the end of the program scan, during that scan. On the very next scan, because it's a one-shot instruction, even though the rung's still true, it's going to execute the false execution and turn it back off. If you compare these four, this instruction has a rung true out on the very first program scan that it sees that memory location go from off to on. Or you could say on the very first scan when this instruction goes from false to true. Then the output state of this instruction will be false on the very next scan and stay that way until this bit memory changes state and then back again. So this goes back to false, and then when it goes back true again, then this will execute again for one scan. The one with the N inside of it for pulse falling edge does it when the bit memory goes off. When the bit memory goes from on to off, that's the falling edge, then this instruction with the N in it would be true for one program scan and one program scan only until the bit memory goes back to the other state and then back again. So it has to cycle states. So in other words, if this were a push button and you were using this instruction, the rising edge, if you push that button, this rung will be true on the very next scan after you push the button. But as long as you hold the button down, that rung is going to go false on the next scan and stay false until you release the button and push it again. This instruction will be false until you press the button and then release it. Now, if you aren't pressing the button, then that instruction was true the last time that the button was released. This instruction right here, the falling edge goes true when you release the button. And I'm talking about a button now, so I'm actually looking at an I/O point. This could be any bit in memory, doesn't matter what it is. This instruction has no idea where that bit is, where it came from, or anything. Now, in your data table, IN00 knows where that bit's at because it points to it. It's an actual I/O which gets its state determined by the screw terminal when you're in the run mode. These two instructions, the P and the N for the coil, this instruction, it looks like a direct coil, but in fact, it behaves like a direct coil because it has a true to false execution, but the true execution can only execute once when the rung N state here goes from false to true. On the very next scan, if this is still true and hasn't reset back to false, then it's going to do the false execution and turn this bit right back off. So if this rung goes true, this instruction right here, output pulse rising edge coil, will turn on whatever memory location it's addressing for one program scan, and on the next program scan, it'll turn it back off. It behaves just like a direct coil, but it can only be true or have true execution for one program scan unless the rung in state goes back to false and then back true again. Just the opposite with this. This could be like a reverse coil, if you like. I don't think that's necessarily a good idea, but basically what this means is if the rung is true, then this is going to do the false execution, but when the rung goes false, on the very first scan that it goes false, this will turn on the bit in memory. And then on the next scan, it's going to flip back to the opposite. Now these two right here allow you to separate out the rising and falling edge trigger detection from any specific type of instruction like a contact or a coil. In other words, this F trigger, you could add this to an equal instruction, to a comparison instruction. You could add it to the Q on a timer. So when the timer first times out, if you use this, you would use this one right here. When the Q goes high, this will put out a true rung out for one program scan, and that's it. If you want to know when the Q falls back, then you would use the falling edge. In other words, you could put this after a Q on a timer or a counter, and it's not going to give a rung true out until that value, the Q from a timer or counter, goes from true to false. So you could say it triggers on a false, and this one triggers on a true. But it separates out that function from any specific instructions. Okay, now looking at your lab, let's save this and download it. Now I should turn on my simulator first. I forget that quite often. Then I'm going to save it and download. Let's look at this. Here's our logic. This is the way it downloaded. Now, depending on whether or not you had input 0, and when we say input 0, we mean whatever field device you've got connected to that screw terminal. Or in the case of the simulator, which you see over there to the right, we don't have input 0 on. Let me tell you this, if input 0 had been on, then this rung probably would have executed true on the very first scan. So there's another idea for a first scan bit, and we'll leave it at that for right now. But in the manual, I'm not going to read through all of the instructions and the comments, but there was a little box with some questions in it, looking at the logic as you see it right now. Input 0 is on or off. Well, how can you tell if one of the bits in memory is on or off in a 1 state or 0 state? The color of the text. Blue is off and red is on. So input 0 is off. Input 1 is off because it's blue. Output 0, is it on or off? Well, it's blue, so it's off. Output 0 and 1 are both off. They're both blue, right? Because remember, those instructions, they write to memory locations, but the graphics on the screen are animated by the state of that memory location. The PREC, is it true or false? That's the pulse rising contact there with the P in it. Well, it's false. The rung in is true, the little red dash that you see there, but its out is false. So there's a true in and a false out. Now, it's not blue, it's black, and that is yet another situation that we'll discuss later. So I wanted to answer those questions to make sure that they got answered in case you're filling in the blanks in your manual. Then on the next page, we said flip input 0 on and leave it on. So I'm going to flip input 0 on. I'm going to do it over here with the simulator, over here to the right. So I'm going to go over here and turn this on. What I want you to notice that these are both blue, meaning that those bits in memory are off. So I'm going to turn this on and leave it on. Notice that output 1 is now on. Now, you've already used the set and reset instructions. Notice they both address the same memory location. The red in those instructions indicate that it's reading that bit as on, and the color of the text. However, output 0, it's blue. If you didn't know any better, you might think that output 0 never went on. Well, it actually did. And that's why we put the set instruction in parallel with the direct coil to prove that the rung went true. If the rung goes true, then that instruction told output 0, you're on. Then the very next scan, it says you're off. I call this a bit trap. And I do this quite often when I'm troubleshooting code that has one-shots in it. Because if you looked at the rung without that set instruction, you would see that the rung is black, input 0 is on, it's red, and output 0 is off, it's blue. So you might look at that and say, well, did it or didn't it execute? What's going on here? By putting the set instruction, latch, around it, we can prove that it went true. The rung went true, and output 0 went on for at least one program scan. And we know that because output 1 is on. In your little questions, did output 0 flash on? Not that I could see, so I'd say no. Now, if you catch it just right, you might see it, but that's going to be extremely rare. Input 0, is it on or off? Well, it's on because the red text, IN00, is red. IN01, is it on or off? It's off because the text is blue. Output 0, is it on or off? It's off because the text is blue. Output 1, is it on or off? It's on because the text is red. The pulse rising contact, is it true or false? Well, it has a false out condition. Now, looking at the state of output 0, can you determine if it was on for one program scan? The answer would be no, because just looking at it, you couldn't determine that. That is, you got to ignore what's right below it, the state of output 1, which proves that it went on. But just by looking at output 0, you would not know that it was on for one program scan. Okay, flip input 0 off and leave it off. So we go over here and we turn off input 0. Notice the state of the rung did not change, but the color of the text up here, input 0, changed. We're asking you the same questions again. The only difference between this box of questions and the one right above it is input 0. It's now off, input 1 is off, output 0 is off, but output 1 is still on because that was a set. It won't change until we reset it. And the instruction, is it true or false? Well, it's false. It's still false out. Because remember, it's only going to be true for one program scan when it goes true for the first time on the leading edge, the pulse rising, for input 0. By looking at the logic, what is the only change indicated, and indicated by what? The only change indicated is the state of the memory location addressed and pointed to by IN00. Press and release input 0. Did this action reset output 0? Well, let's do that. Now it says press and release. So I'm going to press it by clicking. Notice that this instantly went to blue because this rung is true, and the true state for this instruction is to reset that to 0. Now I'm going to release the button. And now we're back to this state of rest. It said to press and release input 1. Did this action reset output 1? Yes, it did. Back to 0. Now it says to put input 1 back on and leave it on. We're going to leave this instruction true, the reset instruction. Now remember, it's blue because the bit memory, OUT01, it's off. So the instruction's blue, but the rung is true. So the question was, is input 0 on or off? Well, look at the color of the text. Input 0 is off, input 1 is on. Output 0 is off, output 1 is off, and the instruction is still false, the pulse rising instruction. Flip input 0 to the on state and leave it on. So here we're going to go back. Now notice I've still got input 1 on purpose. So this rung is still true. Now you see we have something a little bit different here. Remember, last man wins. Did output 0 flash on? I didn't see it. Input 0 is on. Input 1 is on. Output 0 is off. Output 1 is off. And that instruction is false. It was true for one scan and went right back to false. Did output 0 transition on for one scan and back off after that one scan? No, not one whole scan. Last man wins. So when we got into the program scan, this rung would have turned both of these on. This rung would have turned output 1 right back off. So output 1 would never have gone on because, remember, it collects up the inputs, puts it in memory, runs through all the logic, and then it updates the outputs. Output 0, that's a bit memory. That's not a screw terminal. That's a bit memory that's associated with an embedded output memory location. Rung 2 would have turned it off a fraction of a millisecond after it was turned on. So when you get to the end of rung 2, output 1 is off. It never went on. It went on, but only the length of time it took to go from rung 1 to rung 2. Rung 1 turned it off. Rung 2 turned it right back off. So it was on then off for whatever time span, which would literally be a few microseconds at best. Okay, so the question was, did output 0 transition on for one scan and back off after one scan? No, it never went on. Not even a whole scan. But as long as you understand what I'm saying, regardless of what you put down for the answer. Now, if you put down yes, now I think you understand that it really wasn't on for one scan and then back on after that one scan. It went off during that one scan. Does the state of input 1 or output 1 have any influence on the state of output 0? That depends on how you want to look at it. Output 0, it actually did go on for one scan and back off for the next. So resetting the set instruction, in other words, resetting output 1 has nothing to do with rung 1 as far as the pulse rising instruction, and when it's true, it flashes output 0 on for one program scan. That's going to happen no matter what. So just the two instructions in rung 1, the one with a P in it, the pulse rising contact, and output 0, the direct coil, that executes the same regardless of what we do with output 1 and the reset logic. Okay, this is the basic operation of a one-shot instruction. If you want to venture out on your own playing with this, and it's a good idea to do that because the one-shot instruction is incredibly powerful and useful for catching the leading edge or the trailing edge of an event. Now, if you want to know how long the event was, you would have to use a timer. You would have to use probably an on-delay timer and set the preset way out there so there's no way it would time out. And then you would watch the accumulate value, CV they call it, count variable. You could watch that, and on a one-shot function, you could capture that value on the falling edge. So there's a lot of things you can do to determine how long something was true, as well as when it went true. In other words, trigger something when it goes from false to true, and then using the other instruction with an N inside of it, the falling edge, you can capture something when it goes from true to false. We've pretty much sucked all the life out of this little piece of logic, so I'm going to have you save and go offline and we'll put in some different logic. So I'm going to save and disconnect. Here's our new logic. The first two rungs are obvious. True if on, energize output or direct coil. True if off, energize output or direct coil. Then we've got the pulse rising and the pulse falling. What we're doing here is we're giving you an opportunity to see the difference in these four types of contacts. True if on, true if off, pulse rising, and pulse falling. Mouse over it. If you right-click properties, see pulse falling edge contact. And by the way, if you wanted to change it, you can drop down the list and pick anything you want. That's another way of changing an instruction you've already put in and you didn't pick the right one. You can always right-click properties and change it. So we have four different types of contacts: straight up, true if on, straight up, true if off. And then we have a rising edge and a falling edge, or leading edge and trailing edge of an event. And then we're using these four outputs so we can see what's on and what's not on. Unfortunately, unless you put a bit trap in here on these two, you're not going to see these rungs go true and these outputs going on. So let's save and download. Our simulator is running, not faulted. That's a good thing. Before I do that though, I'm going to toggle these off. Here we are downloaded online with all the inputs off. You might be wondering why in the manual we have all of these little boxes with questions for you to fill in the blanks. The reason is to establish the state of everything before you make each change. That way you can go back and look at them later if you need to verify what the behavior was. So to start out, input 0 is off. Input 1 is off. Output 0 is off. Output 0 was off, meaning it never went on. Output 1 is on or off. Well, output 1 is on. That's because the rung is true, because input 0 is off. Output 1 was on or off. I guess that's debatable if you want to really split hairs. Output 0 was off before we downloaded and went into the run mode. Output 2 is on or off. Output 2 was off and is still off. Output 2 was not on because we never had any logic that could have turned it on. Now, if input 0 had been on, then that rising edge pulse could have turned it on for one scan. Output 3, is it on or off? Well, it's off. Now, if input 0 was on and then we went off, it could have bumped output 3 on for one program scan. Okay, output 3 was off. The reason that we do this lineup of questions and this very first look, some of those questions don't seem appropriate. But now that we're going to make a change in our inputs, we're going to turn on input 0. And when we do that, you'll see some changes. So watch these instructions here. Watch the state of the outputs. Okay, now it looked like there was only one change. There was actually more than one, but it looks like there's one. Input 0 is on. Input 0 was off. Output 0 is on. Output 0 was off. Output 1 is off. Output 1 was off and it's still off because remember that's a true if off instruction. So even though input 0 is on, output 1 never went on. Output 2 is off. Output 2 was on for one program scan. Output 3 is off. Output 3 was off. We wouldn't see output 3 go on for one scan until we turned off input 0. Putting the bit traps around these one-shotted functions, in other words, around output 2 and 3, where you set bits to see that it went on, that does help. But we're trying to squeeze you through considering these just from an understanding of how the functions work. The black elements are there because of the nature of the one-shot. Remember, we mentioned that earlier. You're used to seeing when you're online blue and red. Blue for false, red for true, and red for on, and blue for off. Now we've got black rung elements. Of the 4 contact instructions, by the rung number, what is their current true-false state? Rung 1 is true, rung 2 is false, rung 3 is false, and rung 4 is false. Now, you say, well, they're not blue. Well, they're black, and those are one-shot instructions, and those instructions would only be true for one program scan, which is long gone by. By looking at the image on your computer, these 4 rungs list 2 elements that allow you to discern the on-off state of input 0. Well, first of all, the red text, correct? That says it's on. But you can also say that the true if on instruction is true. That says input 0 is on. And the true if off instruction is false, which tells you that input 00 is on. Okay, I told you don't leave this logic until you've exercised it enough to have a firm grasp on these 4 contact instructions. True if on, true if off, pulse rising, true, pulse falling, true. Save, go offline. Well, I just couldn't help myself. I talked about this in the discussion, but it wasn't in the lab project. So what I did was, remember I told you if you want to determine when the Q on the timer went high, and that's of course when the ET equals the PT. The elapsed time equals the preset time. I might have accidentally called it CV in the earlier discussion. I meant ET, when the ET is equal to the PT, then Q goes high. And what I did was I put in a rising trigger and a falling trigger, each to 2 outputs, one that's just a direct coil and the other that's a set coil. That way we can prove that those 2 instructions did go true. One when we reach Q, true out, and so we'll do that. So I've got this for 1.5 seconds. That's long enough for you to see it accumulates. I'm going to turn on input 1. So I want you to watch the false state out of Q go true, you won't see anything happen here or output 4, but you will see output 5 set, and that proves if this went true in set 5, then this went true in set 4. Even though when it came back around the next scan, this might still be true here, but this is false after one scan, so the false execution of this direct coil turned output 4 back off. So let's turn on 1 and then watch 4 and 5. You see, you didn't see 4 go on, but you see 5 is on, which means it did get set. So you did have a true out of this rising trigger. Now I'm going to toggle this back off. I didn't bother putting in logic to reset it like I did in some of the other code. Q is still on because the timer hasn't reset. Okay, so this is still true coming out, but this is a one-shot rising trigger. I'm going to turn input 1 off. Q will go false out, and you'll have false into this rising trigger and into this falling trigger. The rising trigger doesn't care. It's looking for a false to true, not a true to false. This guy down here, it's looking for a true to false. And if it does as I told you it would, then it'll turn on 6 for one scan and it'll set 7 just to prove that it did it. So I'm going to turn off 1. In the instant that I do, Q went false because we reset the accumulate. In other words, the ET went to 0, so they're no longer equal. This went false. False into this instruction. It catches or one-shots the falling edge of Q. And we know that output 6 went on because output 7 is set on. I just wanted to throw that in there because I did, bring it up in the discussion. I went off chasing a rabbit, and there you have it. Now, we're not done with this lab project, but because of the length of time that we took to discuss it up until a certain point, we were trying to exhaust all the possible combinations of coil, true-if on, true-if off instruction types with pulse rising, pulse falling, and some of the coil types. But we're not done yet. So we're going to stop here and then continue on in the next lab project, looking closer at the coil types.